A very good morning, all of you. So, in this class, we will learn about, as we discussed last time, sequential circuits. But before starting, let's have a quick recap on what are combinational circuits. Fine. So, in combinational circuits, what you have is you have a few inputs, a logic, and output. And here, the output depends on what are the inputs at present. So when you have the output which only and only depends on present state of inputs, you can call such a circuit as combinational circuit because only the combination of present state of inputs will determine the output. Now, in sequential circuit, you have a combinational circuit like before. This is, I can say, your combinational circuit. Plus, you also have, let me just try it like this, a memory element. So you have a memory element as well in addition to the combinational circuit. So what will happen because of this memory element, unlike the combinational circuits in which the final output was dependent only on the present state of the input, here the output will not only depend on present state of the input but also on, I can say, but also on the state of the memory element. And what does memory element takes in? It takes in actually the past state of output. So when your final output depends on present state of input as well as on past state of output via memory element, such a circuit is called as a sequential circuit. If somebody asks you what are the examples of combinational circuit, as we have discussed in offline classes, you can say that combinational circuits are all logic gates. We can call all logic gates to be combinational. Say, for example, logic gates of two input NOR or AND gates. Here we see that the output changes as soon as the input changes. Or another example of combinational circuits can be adder and subtractor. Here also we see that when we are making truth tables, the output suddenly changes as soon as we change the present state of inputs. Yet another example can be multiplexers, demultiplexers, encoder, and decoder. So all those circuit in which the concept of memory was missing, but it was having certain kind of logic such that the present state of input would govern the present state of output, we can call all those circuits to be combinational circuits. Fine. Now we know that combinational circuit plus a memory element is sequential circuit. So the essential task now become to understand what is memory. Okay, what it is and what it has to do with digital electronics. Actually, memory is having the same concept as we have in our daily life to remember things. And you can remember things only if it had happened in the past. That's why I'm saying that the past state of the output is to be memorized by memory. It is same as having what we call as yadasht. I told you something, you remember it. For example, I told you a fact, let's say fact 1, that sun rises in the east. This is one fact, and I have told you this fact so that you can remember it. Now, if I've told you this fact, I should be able to do something with that. And what I should be able to do is that a good memory, something which we can call as a good memory or एक अच्छी याददाश्त होने के लिए या हम कह सकते हैं the features of good memory comes with three important aspects. The first one is whatever the block of diagram you're calling it say as memory element, it should be able to hold the value. मैंने आपको एक बात कही कि सूरज पूरब से उगता है, तो आप इस बात को याद रख सकते हैं. You should be able to hold the value. Hold is an important aspect. Next comes we should be able to read the value. जब मुझे जरूरत पड़े कि मैंने तुम्हें क्या बात बताई थी बताओ, then I should be able to read that value. अच्छा मैंने तुम्हें ये बताया था कि सूरज पूरब से उगता है. And by chance let us consider मैंने आपको एक fact 2 बता दिया. Let us consider that fact 2 is that the sun rises in the west. And your whole task was to hold the value. I told you fact number 2 that sun rises in the west. And मैंने आपसे कहा कि what is fact 2? You say that you told us कि सूरज पश्चिम से उगता है और the sun rises in the west. तो आपने होल्ड कर लिया और मैंने रीड भी कर लिया बाद में आपसे पूछकर. बट फिर मुझे पता चला मैंने तो आपको कुछ गलत गलत बता दिया था. So the third concept which comes in that is that I should be able to change the value. Change is an important aspect. So you can remember that the three golden stars of a good memory are HRC. You should be able to hold the value, you should be able to read the value, you should be able to change the value. Fine. And that's how the concept of memory comes into picture that I want to, let's say in digital terms, my data is stored in form of bits, which are nothing but binary digits that can be either 0 or 1 at a time. And I want to store the value of bit. For example, I want to find out what was my bit 1 earlier, and I have told that it is 0. So I should be able to read this 0, and if I want in later or in future, I should be able to change this value. One particular implementation can be achieved by using cascaded NOT gate. So I hope you're all aware about the logic of NOT gate. You give it some input, let's say A, and as an output, you will get A bar. Now, if I cascade the output to another NOT gate, I can get A back. And now, if further I would feed back this output to my initial input, then I know that it is some sort of an oscillator. This A goes to A bar, and then this A bar will that turn A. This again fed back to the input, it would remain A. So in a way, in this particular loop or cascaded NOT gate, I am able to hold a value because this is one input gate. I can say I'm able to hold a bit. If I would make A equals to 0, A bar would become 1, and then again A bar would become 0. So I'm able to store 0 inside. Now, whenever I want, I can also read the value. I can read the value by connecting a multimeter probe or connecting an LED over here. Unfortunately, in this particular case, changing the value is going to be tricky, or I can say it's not possible, because if I want to make a change over here, not only I am feeding some output, some input from outside to an input of a gate, but also I'm feeding the same to the output of the other gate. And this would go wrong in terms of electronic circuitry. Therefore, I can satisfy the criteria of holding a value and reading a value in this particular cascaded NOT gate configuration, but changing the value remains a trick. And then comes the concept of what we call as latches. So now you can write another heading. We are going to study about latches. Latches. So latches, I can say, are the building block of memory elements, building block of memory elements with all the three properties. Unlike all other gates, here we would proceed with making the diagram first, and then later we will analyze its functioning, that how it would satisfy the criteria of being called a good memory. So make two NOR gates. In these NOR gate, you know that it would have one gate, each gate would have two inputs, and from here I can take one line. Is it possible? Yeah, I can take that. This is here. This is going to be the output. This is going to be the output. And this is the input. Fine. Actually, what I am interested in is that I want to feed back this to this here. And I want to take that and I want to use it like this. So in a way, I can say that let's say this output is called as Q, and this output is going to be the complement. I will tell you later why I'm writing all these stuff. So in a way, I can say that this Q bar is going and being fed to this gate, let's say 1, and this Q is being fed to gate 2, and this input I can say S, and this I'm going to call as R. Fine. And these are what type of gates? These are nothing but my NOR gates. I'm only using NOR gates, but this particular connections or the circuitry will help me achieve the sequential function. Although I'm using only combinational NOR gates or combinational logic gates, but I would be able to achieve sequential function just by making this circuitry. There's a special motive behind writing this S and R and not just any other letter. You will get to know in a few minutes. This Q is an output, and this Q bar is going to be the complement of the output 1. So there is one rule associated with this particular circuit, and that is that Q, if is going to be 0, then Q bar has to be 1, And if q is going to be 1, then q bar has to go to 0. Fine then. Now you see that in one particular time, this q bar will be fed to gate number 1, and then it will produce this q. So I can say that this particular input is nothing but q bar, and then when this q bar will be fed along with this r to the first gate, I will get my output, which is q next, which I would get later on when this q bar would be fed in. Similarly, I can say that q was fed in as the input of gate 2, and I would get q next bar. Don't get confused with it. Later on, q next bar would be fed in, and then you would get q next, and q next would be fed in, you will get q next bar. So this cycle would continue, but let us see what will happen if the output becomes stable. But that is the thing which we would analyze in due course of time. First of all, try to collect whatever we have learned in the past. For example, what are what is the truth table of NOR gate? So in NOR gate, you have A, B as inputs and Y as output, let's say. So you know that in NOR gate, the output is 1 when both inputs are 0, and in rest of the cases, the output is 0. Fine. You have to remember this thing. And also, how I can write that what is going to be my Q next. So my Q next is nothing but it is going to be equals to R plus Q bar. If you want, I can write a minus sign over here, a minus sign over here, just to know that this is for the past input or the past state of the output. So I can, or I can write it as Q current. What is the current Q bar? What is the current Q? And this becomes q next. So q next depends on r plus what is the current state of q prime and whole prime of this thing. Similarly, q next bar depends on what is s and what is q current, and since it is going to be an output of a NOR gate, so I have to take prime again. Now, like all logic functions, it is a two input device, so we can have four combinations. So you see that from here we are only having two inputs, we are getting two outputs. So case one can be keeping r equals 0 and s equals 0. Fine. If I do that and I put r equals 0 and s equals 0 in this equation, you would see that the final equation for q next would become 0 plus q 0 plus q current bar whole bar, and because 0 plus anything is that particular thing, I would get it is equals to nothing but q current bar ka bar, and that is nothing but q current. Similarly, if you write for q next prime, if you write for q next prime, it would be 0 plus q current whole prime or whole bar. So this would be nothing but q current bar. So q current will be same as q next, and q current bar will be same as q next bar, or I can say that q next would be same as q current and q next bar would be same as q current bar when I have both inputs as 0. So we will see what will be the implications of this when I would actually put in the values of r and s equals to 0, keeping in mind that q can have one state and q next can also have one state. Actually, in terms, it is called as a no change condition. A no change condition. And why it is called as a no change condition? Because the next state is same as the current state, the next state of the q current bar is same as the next state of q next bar, or the state q next bar. That's why we can say that it is a condition of no change. Now we can have another case, case 2, when my s equals or becomes equals to 1 and r becomes equals to 0. I will use the same logic. I would put, let's say, s equals 1 in this equation. If I would put s equals 1 in this equation, let's see what would happen. I know that my q next prime would then become equals to 1 plus q current whole bar. And I know that 1 plus anything is 1. 1 bar is equals to 0. So actually, q next bar becomes equals to 0. And with the rule which we have kept earlier, that the rule is when q equals 0, I want q bar to be 1. Or when q equals 1, I want q bar to be 0. So if I have q bar or q next bar equals to 0, I would have q current, or sorry, q next should be opposite of this. So 0 opposite is 1. That's why I would get 1. So this is case 2. Because let's say whatever the condition of q current was, it is now, it seems as if it is not dependent on q current. So I can say that if I would make s equals 1 and r equals 0 in my upper circuit, which is shown over here, if I would do that, what I will get is my q next will be equals to 1 and my q next prime will be equals to 0. And because here q next is equals to 1 is what is the output we have got, we can call that this state is a set state. And this is what s stands for in this particular circuit. When you would make s equals 1 and r equals 0, you will get q next equals to 1 irrespective of what was the input, what was q current, what was q current prime. Your output is going to be equals to 1 for always, and we call this as a set state. Let me add another page to study what is going to be the case 3 then. So let us now study case 3. I hope you must have got an idea. Now, instead of making s equals 1, I would make s equals to 0 and r equals to 1. And as you are aware of uh, from these equations, where we are having those equations there. Yeah. So we had q next equals to this and q next bar equals to this. So I would use q next is equals to r, which is 1, plus q current prime whole prime. I know that this is nothing but going to be what? This is going to be 1 plus anything is 1, prime is equals to 0. And if q next is equals to 0 with a rule which we have already set, q next bar has to be equals to 1. So in this case, no matter what the current state of the output was, what was q current bar or what was q current, what we are getting as output is q next equals to 0 or q bar next equals to 1. And because the output is now becoming 0, q which is our main output bit is becoming 0, I can say that the state is of the reset, and that's why I used this letter s over there. This letter s and r. So if r is 1 and s equals to 0, I would get a reset condition. My output would always be 0. The last case which is now left is case 4. What will happen if I will make s equals to 1 as well as r equals to 1? So as per the equations, I would have q next equals 1 plus q current bar, and then I would have whole bar, and this would become 1 plus anything is 1, bar should be equals to 0. And as per the rule, I can say that as per the rule which we define, my q bar next then should have become equals to 1. But let us check in actual essence what has happened, because r has also equals 1, r is also s is also equals become 1. So I would have q next bar is equals to s, which is 1, plus q current. Let's say, are we moving right on the formulas? Uh, um, so for S, it is S plus Q current. So I would have Q next bar is equals to S plus Q current whole bar. And this also become 1 bar because 1 plus anything is 1 is equals to 0. But our rule says that the Q next bar should have been equals to 1. But our input says that no, it has to be equals to 0. So because it is defying our rule, we would say that this particular input state, S plus S equals 1, oops, can I choose that? This particular input state, S equals 1 and R equals to 1, is forbidden, is actually forbidden. Because this leads you to a place when your output will become out of control. Because we want Q to be opposite of Q bar or Q next to be complement of Q next bar, and that would cause a problem. That would then make a problem. Fine then, that would make a problem. Now, what we can actually do is we can summarize all of our results in form of a truth table in which you have an input S, you have an input R, and you want to find out what is Q next and what is Q next bar. So we can formally make this particular table by, let me just take a rectangle. Uh, um, this is, uh-oh, I want to make a rectangle and not just do that. I want to take it in. I want to take this in. Oops, sorry. Yeah, I want to draw a rectangle because I want to make a table here and I want a few lines now. I want Q current, I want Q current prime, I want S, I want to know what is going to be the state of R, I want to check what is Q, I want to check what is Q bar. And let me just change the color of my pen. So let's say this is Q current. This is Q current bar. This is the present state. And I have S, R. I want to check what is going to be Q next and what is going to be Q next bar. Here, Q next bar. Fine. So I can have first condition when my both inputs are 0, 0. So I can have both as 0, 0. Here, let me just make a line here. Fine. So one condition can be that my Q current is 0 and Q current bar is 1. The other condition can be my Q current is 1 and Q current bar is 0. Because this is 0, 0 and I know that as per case 1, so this is going to be the output for case 1 when I put S equals 0 and R equals 0. And I hope you remember that in that case, Q next was equals to Q current, that is 0. Q next bar was equals to Q current bar, that is 1. Or in the other case, you can see that it is going to be Q current equals Q next and Q next bar equals to Q current bar. And this is the condition of what we call as no change. Fine. You see that the state of the output has not changed here when we are keeping both S and R equals to 0. Fine. Now let us check another case when we have S equals 0, R equals 1, S equals 0, R equals 1. Let us check that what would happen in this particular case. I can have input as 0 or Q bar is 1. This can be 0, this can be 1. You see that whatever the input be, if R equals 1, we were getting Q next equals to 0. If R equals 1, we were getting Q next equals to 0. And if Q next equals to 0, we were getting Q next bar to be 1. And this was for all cases. Fine. Irrespective of what the input is. If my R is 1, I want my output would eventually become 0. And you see that this becomes the condition of a reset. When R is 1, R stands for reset, we get my Q bar to be Q next to be equals to 0. Similarly, for the other one, I can have it like this. Let's say this is the possible combination of input. I have S1 and R as 0, irrespective of what the inputs are. Q has to be 1 and Q bar has to be 0, and we call this as set condition. Fine. And these are all what we want. Next is when what will happen if I have my inputs like this, no matter what the present state is, I would fall in a pit, and we call this condition, which is forbidden, as a race condition, and I would get an unpredictable output. And this is forbidden. We won't give both inputs to be equals to 1. Whatever we have done till date, or अभी तक जो भी हमने किया, is SR latch. So latch has a meaning which we call as something which holds. जैसे दरवाजे पर लैच लगाने का मतलब है दो दरवाजों को एक दूसरे के ऊपर रोक देना, कुंडी लगा देना, इज कॉल्ड एज लैच. इसी तरीके से आप देखें यहाँ पर इस सर्किट में एक तरीके से एक छोटी सी गांठ लगा दी गई है, and we can call also call that as a latch. You see over there, yeah, in this particular circuit. Oops, I'm very bad at it. Let me just handle it. Yeah, this one, where it is. Yeah, still, yeah, this one. You see over here in this particular circuit, we call this as latch because ये एक दूसरे के जैसे गांठ बंधी हुई है उस तरीके से काम कर रहा है. And this particular element provides all the three features of a good memory. And I hope you remember what are those features of good memory. I can hold a value. For example, I want to hold a 0. I would make 0 hold करने के लिए I would make s equals 0 and r equals 1. And I now don't want to change it, so I would make s equals 0 and r equals 0. So I would be able to hold my value. And if I want to change it, I can make s equals 1 and r equals 0. So this would store q equals 0. This would hold q equals 0. And this will help me change q equals 0 to q equals 1. So what I have got is this. I have got a block in which I have two inputs. I have got a block in which I have two inputs. One is S, another one is R. One is S, another one is R. And let's say I have got two outputs. One is Q, another one is Q bar. And let's say I only am interested in finding out the state of Q. So this is the final state which I'm interested in. And I want to make this equals to 0. To do that, I can make, if I want to make this equals to 0, what I'd do is I would give r equals 1, s equals to 0, this will automatically become 0. And I want to keep it as 0. So there are two options, either I keep this input as 0, 1, or I keep as 0, 0, then I know that my output will not change. But if I change any one of these bits, let's say I would make this bit to be equals to 1 now, then my output will change from 0 to 1. So all the features of a good memory, I should be able to hold a value, store a value, or change a value, I'm getting using this latch. With one condition, with one constraint, which is that my s cannot be 1 when r equals 1. And this state is forbidden because then we will fall in pit of unpredictable outputs. Fine. This is all for my side from combinational circuits. We'll learn more about latches in our next lecture.